we start off thinking, well, we start off here, right? We start off with a diagram with a level controller indicated just like generically. We then move into this mathematical abstraction. And what I want you to remember is that beyond the mathematical abstraction, there's actually even another layer, which is kind of hard to draw, but which is a much more physical version of that same diagram layer, right? So a real tank would obviously have actual dimensions, right? A real tank which has real walls. And then if you zoom in and you ask yourself, so how is it that this level is being measured? You'll find that there's a whole host of things. Let's say we could maybe use something like a ball float that's in your cistern in your toilet to measure this level. So if this was the kind of, if we zoomed in on that corner over there, we could say, well, there's a liquid level, and actually on the side of that vessel, there's kind of an arm that's actually physically, mechanically connected. That's floating on top of that liquid level. And that's kind of the one place that I want you to go to when we think about this larger scale of control practice, right? That in reality, on a very large flow sheet, and you can imagine that if in the end of this, at the end of this theme, we're going to be drawing all of this on a document called the PNID. And a PNID contains a full set of very detailed drawings for every piece of equipment that's on in the control scheme of a plant. And you can imagine that on a plant where we have maybe several distillation columns, some kind of a settling tank, some recycle and so on, the list of actual equipment that is available on that site is actually kind of mind-blowing. So you've got to think that at some point, a person has to specify the actual mechanical details of every time we casually write something like LC. That corresponds to an actual physical principle, which corresponds to an actual piece of equipment that needs to get ordered from an actual manufacturer, delivered on site, installed appropriately, and so on. And so on the one hand, I'm asking you, we start now on the very zoomed in level, on the reading, right? So I'm taking you on this trip going from the very, very low level of what it means practically of implementing a controller, right? Using mechanical measurements, and also, in this part, you also learned about, and I think you should have learned about this already in quite a bit of detail in your CIO subject. But again, when we draw an icon like that, we actually think of a physical control valve, a ball valve typically, which has a physical stem and all of this kind of stuff. Remember, I had one of these in class during one of the tutorials. And so on the measuring instrument side, every measuring instrument has a principle by which it works. It has its own dynamics. It has its own kind of limitations in terms of how much it can measure and so on. There's a transmission network that then transmits signals from there to the controller. There's a controller which we've analyzed in great detail, but which will actually take the form of some physical hardware, whether that is a PLC, programmable logic controller, or whether it is actually distributed control, a piece of hardware that you could buy off the shelf called the PID controller. That's then connected to a final control element. That final control element then is actually physically wired in or bolted into the plant. And all of that is kind of what we're thinking about in Chapter 8, right? So In chapter 8, we're learning all about how these physical things work. So then we start zooming out, and kind of, I think one of the useful ways of thinking about the journey that we're taking is we're kind of doing that Google Earth thing, right? So we're starting on this very low level, zoomed in level, where we can actually just see each of the pieces of equipment, right? And then we start kind of zooming out, and as we zoom out, these little details, this kind of detailed valve drawing is replaced by a icon, and this detailed drawing of the actual level measurement is replaced by just that line, and then we kind of zoom out and zoom out and zoom out until we can see the full flow sheet. So in chapter 9, we're talking about the conceptual layers of process control, where we're actually starting to think of not just designing a single controller or even groups of controllers, but thinking about the entire control philosophy on site. So chapter 8 was all about these low-level things, and chapter 9 is all about safety and reliability. Choosing the correct pieces of equipment based on their reliability and based on the layers of safety that they identify in order to make sure that the plant is safe. Now, to spend a little time Googling this guy, the Bhopal disaster is one of the kind of shameful incidents of our industry. It occurred in 1984, and it's basically the world's worst industrial disaster. It involved the release of methyl isocyanate. About 500,000 people were exposed. It happened in India. There had been a sequence of events of safety failures on the plant, and this methyl isocyanate was released. This big wave of the gas kind of went around and overwhelmed. Something like 2,000 people were killed on the day, and just hundreds of thousands of people were affected. There were lots of injuries, and even today there's a lot of birth defects. And the reason why I'm saying this is that I want you to really really get a full grasp of the impact of chemical industries. Like 2,000 deaths, 500,000 affected. You may imagine that you'll be able to keep yourself out from well, I'm not going to go into dirty industry making bad chemicals, but have a little bit of a Google powder explosions. So one of the other very big kind of causes of death in industry that is not widely known, but these powder explosions can happen in flour processing facilities. So that's flour that you make from plants, right? So this is not a dirty chemical. It's not something terrible. If I asked you, nobody would be scared. Well, okay, maybe if you're some like super gluten intolerant or whatever, but few people are afraid of flour. And these flour explosions, dust explosions that happen in flour processing units lead to the deaths of many people every year. And it's all due to a lack of focus on safety. One of the things that we promise to do as engineers, and I signed a declaration as a professional engineer, EXA declaration, that is all about promising to behave safely and treat, kind of make sure that my designs are safe and not promise that they are safe if they are not safe, and so on. But the introduction of the OSH Act, and you can also kind of Google a bit on that. The Occupational Health and Safety Act, widely known as OSHA, we have to take safety into account in a reasonable way. And actually, we take the approach that every death is avoidable. And so because of that, we have these layers of security that we introduce when we talk about control. Now, we've only been talking really in this subject about the continuous aspects of control, controllers that look like this. But Chapter 9 asks us to think a little bit broader and ask questions about what happens if this level controller fails to keep the level below the lip of that tank. What happens if there are toxic chemicals that are in that tank? Do we have a physical kind of a bunting, some kind of a thing that the tank can flow over into? Are there alarms placed along the top of that tank limit that will alert personnel that high-level situation is about to occur? So in other words, the level controller can only do so much in terms of like maintaining that level. There's a whole other system outside of that, which is called the interlock system or alarm system, right? So basically, the structure that we're following here is that we design a process, and ideally we would design that process, to already include some safety measures like bunting. There's a level controller here, which is part of the continuous control system. And then on an outer layer, so this is what is often called base layer control. And you'll see in the diagram in the book, there's kind of what they call the design. There's design on the inside, that's design a safe process to begin with. Then we add base layer control to make sure that it stays safe. Then we add on another layer around that, we add things like alarms. And sometimes it depends on how you think about this, but it may be in this layer, or it may be in this layer or in this layer. There can be an interlock system, for instance, that stops pumps from pumping when levels are high, or automatically closes valves. So these are digital controls. Then we have this kind of supervisory control over there. Then we have automatic actions. Then we have physical protection. And physical protection, for instance, just to give a different example from the tank, that would be something like fitting a pressure vessel with what is known as a PRV, or a pressure release valve. And so these guys take the form of typically what is called a bursting disc. In other words, it's a cylindrical kind of, or a flat surface where we have an area over here which is rated to a certain pressure, and so that is designed to rupture. Right, so that bursting disc has now ruptured. So as pressure goes up in this vessel, that little valve on the side is typically mounted in such a way so that it can be replaced if it bursts, so that you don't have to throw away the whole vessel. And so that means we've got a mechanical safety device. Now, kind of in the opposite direction of that, we also have things like vacuum breakers. And so you may be aware, and so these are also kind of mounted on vessels. I think the nicest version of this is you can also Google this. There's some really nice video of a rail car imploding. So if you Google that, you will find kind of a video of a rail car. So these are like these kind of large scale liquid conveyors. And basically the problem that the vacuum breaker is supposed to alleviate is that you imagine that when you empty this vessel out, it's empty. But actually what it contains in many cases is either air, or if you forget to leave this entry port open, and you have a small amount of liquid lying at the bottom of that rail car, on a hot day, that can actually evaporate. And if you close that lid and then these things condense again, you can snap one of those rail cars. It's actually kind of fun to watch. I have a whole host of them, but like if you Google them, you will see kind of crumpling, these huge vessels just crumpling like you would crumple a Coke can. So this is what these physical protection devices entail. Then after that, so now I want you also to understand that these layers are not necessarily dependent on one another. In other words, the physical protection layer, this continues to work. It's a mechanical device, right? So that rupture, that bursting disc, or the vacuum breaker, all of those things exist at the same time as the alarms and the automatic action and the base layer control and so on. And they are designed to make sure that you kind of hit one of them. So in other words, the priority is we design a process that is intrinsically safe. Most of the time, the base layer control keeps everything within control, right? When there is an alarm, alarms should only occur during abnormal conditions. And automatic action should only take, like, override the actions of controllers when there have been alarms and so on. And the physical protection should only be relied on, because you can imagine there's like, you have to stop the plant if you if you burst a disc, right? The physical protection is kind of a last layer of defense. Now, if all of those things fail, we need to make sure that we can still not kill people by having proper emergency response. And if we cannot keep the damage localized to the site, we have to make sure that the community understands that they are living near in a dangerous area and that they need to be able to respond if and when things go wrong. So that's basically what we're trying to get across in terms of the layers of protection in Chapter 9. And the rest of Chapter 9 kind of details a whole lot of different ways in which we can design these things. You know, so what exactly is a safety instrumentation system? What are the things that are different about what are the things that are different about normal base layer control and the interlock system and alarms? How do we design alarms in a rational way so that we don't overload personnel? Actually, one of the interesting things about Bhopal is that they also, and another place to kind of Google is the very famous 3 Mile Island. So at 3 Mile Island, they had what is known as an alarm cascade. And I think for those of you who haven't actually been in a control room before, it's important to understand that in most cases, the operators are sitting, modern operators are sitting in front of kind of panels, lots of screens, basically, right? There used to be kind of the old version of this used to be kind of lots of like a mimic on the wall, but these days, operators will be sitting in front of a desk. There'll be a chair over here, and the operator will be interacting and watching these screens that have little pictures of the plant on. But that control room typically is not fitted with windows, and is typically also, depending on the kind of what you are making on the site, if it's a really dangerous chemical, you will typically find that the control rooms will be blast proof, and in many cases they'll have a double door system so that operators can go in and out. But the upshot of that is that it is actually very difficult for operators to know what is going on outside of the control room. I remember when I was working at Sasol, they would often only know, for instance, if it was raining by observing that one of the temperatures went down on the trains, and then okay, it's probably raining outside, so we can't go out now. Inside of the control room, you are completely reliant on the instrumentation that you have of the plant. So that's one big problem, is that you only know that something is happening because somebody has actually put a wire going from that place into the control room. Otherwise, you wouldn't know. Well, there's one other thing, is that some people, obviously there are, in some cases, people, they will be kind of in communication through radio, typically, between the control room. But that's one person maybe roaming through your unit, and you don't actually know everything that's going on. Now, so what is the problem with alarm cascade? So I'm sitting here, and a little alarm pops up on one of my screens. I have to touch a button or click on that notification to make it go away. And it's a little bit like when everybody joins at the beginning of these Google Meet meetings. There's 100 alarms at the same time. When we put these alarms in, it's unrealistic for somebody to take action on an alarm other than just dismissing it at the rate of more than about 7 per 1 every 7 minutes, right? So if you think that an alarm should give the operator time to react in a way that will make bad things not happen. So let's talk that through, right? So let's say we want to put in a level alarm. We've got a tank here. Normally the level controller is working fine. We want to warn an operator of a condition where the level is dangerously high. The novice version of that alarm has the alarm just right at the lip, at the top here, saying, hey, it's super high, the level is too high, okay? The problem is that if it's right at the lip, by the time that the operator can take action, close a valve or open a valve or stop a pump or whatever, the tank has already overflown. So an intelligent alarm happens well before the limit. So if we were drawing kind of the level creeping up, let's say this is overflow. Now, also keep in mind, these guys are watching. There's not just one level. There's 100 tanks maybe on the site that maybe they're watching one unit. Maybe there's 10 different levels that they have to watch. But they also have to watch temperatures. They have to watch flows. They're being screamed at because the production rate is too low. So they're under a lot of stress. And this level is creeping up. At this point, at this overflow level, bad things happen. Ideally, if you know that the rate, if you predict that we're going to reach a bad place kind of in about 10 minutes, that's the time when you raise the alarm, right? Because if you think that the operator has time to take action, if the level was going up and it takes more than 10 minutes to stop that level from going up, and why would that happen? Maybe it takes time to close the valve. Maybe it takes a couple of minutes just to understand which level it is, which valve to actually close to make that happen. So you kind of in that 10 to 5 minutes region is when you want people to interact, or they need to take action. Now, you know, the alarm gets pulled down, the crisis is averted. If you have another alarm happening at the same time, right? So now you see the guy's taking action, and there's another alarm that says, no, you know, it's really bad now. It's even worse. In 3 Mile Island, they were getting something like 100 alarms per second. Now, it's obvious that if you're getting 100 alarms per second, there's no way that you can action all of those alarms, right? But there's a very distinct reason why this happens, and it's a little bit due to the way that software works. These days, the way that you kind of build these alarms is not by purchasing an actual physical alarm. Typically, what you will do is you'll have an alarm that's set up just to be kind of within 90 to 10% of the full range of the measurement instrument. And those defaults get dragged and dropped onto the flow sheet. And so there's two kind of important things that we've learned from the way that people set up sheets. The most common PID settings are 1, 1, 0. And the reason for that is because that's the defaults, right? And too many alarms. Now, this means that this kind of explains why there's an industry stat that says something like 30% of PID controllers, if you turn them off, control gets better. And at the same time, we have too many alarms because they come in by default, but we have to have a meeting to take them off. And this ratcheting effect leads directly to alarm overload. Now, rational alarm design, if you get two things out of Chapter 9, it's that safety is incredibly important. We know to a great extent how to make things safe. But at the same time, because safety is not as measurable as things like downtime or throughput or whatever, safety is often thought of last. And if you can leave yourself with one big thought, if I can leave you with one thought coming out of this, is that safety should be top of mind at every juncture when you're designing controlled systems. We haven't talked about safety as much in this module because we focus mostly on the design of controllers, individual controllers. But when you think about interactions between controllers, that's when safety really becomes important. So you need to situate your control design within these layers of protection. Make sure that you consider all of these things. And for those of you thinking this may be kind of like a very abstract thought right now because you're not going to be directly assessed on this in this module, remember that this is exactly what you will be doing for the large-scale control project in this module, and also which will be kind of a small version of what you'll be doing next semester during the control design for your final year project. Now, I hope that's given you kind of the overview of chapters 8 and 9. Like I say, there's a lot of like bitty detail in there, but don't focus so much on. I think engineers are very drawn to the calculation aspects, you know, the mean time to failure or whatever. But I would like you to Google these two disasters. Think about how they could have been avoided, right? The Bhopal disaster, partly by better design, and something like 3 Mile Island, where we have classic failures of alarming, by considering more rational alarm design. And you'll already be in a good place, right? When you feel the weight of 2,000 deaths on your shoulders when you do design, that's when you have the appropriate level of respect for the design of a plant. Right, we've got a couple of minutes left for questions. Are there any questions? Justin, if you could maybe just read them for me, that would be super useful if there are. Oh, wait, here we have.
Yes.
Flare system. Okay, flaring is actually, in many cases, flaring is controlled release. So flaring is a little bit, it's not quite like physical protection, because flares are often actuated. So they don't actually fall under, flares are typically not used for protection in the same way that these bursting discs are. So bursting discs are, or let's say the characteristic of the physical protection layer is that they are completely autonomous and that they are completely physical in nature. In other words, they operate without actuation, without any additional input. Like if the control system falls down, if the pneumatic system is down, if the electrics are down, the physical protection systems will still continue to function, and they will all continue to function independently. So most flare systems are simply valved. In other words, they are actuated. They're like you would put a valve in here, except that valve goes into the atmosphere. And then the flare system itself, in order to actually make it a flare, and so maybe for those of you who are not familiar, a flare system, you've seen these, if you've ever been to Sasol, you've seen these very, very tall towers, and then there's this massive kind of flame here, right? Now, if you think about how that actually works, there's a whole ignition system. Right, so there's a pipe, but kind of at the top of that flare, there's a whole kind of thing that says, I need to be able to actually switch on or combust that gas, which means that I need kind of special nozzles. I need an ignition system to make sure that the gas combusts. I need to perhaps mix in oxygen or design something that's like a automatic pulling in system, and I need to actually have and somewhere at the bottom here, there is a valve. And so most of the time you flare only under duress, because it's actually like you are losing material that you would rather retain. So the flare system is kind of a space of last resort, but you can think of it almost like the flare system is almost like going to a drain. Right? So you could say, well, there's some circumstances under which I will kind of get rid of material and I will pour it into the drain, right? Now, the flare system is like pouring, it's like a drain, but into the air. And so it's kind of undesirable, and people don't like flaring. You shouldn't design it so that you need flaring all the time. It's always better to avoid flaring if you can, but they're also not physical protection, because they are in most cases not completely automated systems. So for instance, there's a lot that can go wrong with the ignition system, there's a lot that can go wrong with the valve actuator, and so on. So I hope that answers that question.
Someone asked then if it falls under base layer control.
I think it's important to distinguish the control system that would be writing to this valve may be part of base layer control, right? But it will probably be a system that's tuned in such a way so that valve is closed most of the time. So some like the systems that we've discussed, the override systems or the selector systems, where there may be a controller which is connected to that valve, but is kind of also writing to another valve which takes the same stuff to kind of a gas reservoir, for instance, right? And so most of the time, what you're trying to do with the flares, you're trying to get rid of material. But in most cases, you'd rather store that material and then reuse it later. And so, yes, in most of the cases, that would be the normal operation would be base layer control. But like it's important to kind of also distinguish between the flare itself as a piece of equipment and the control system that controls the amount of stuff that's actually sent to the flare.